go through this. Okay, so we were talking about JK flip-flop in the last online lecture, and we looked at this characteristic table of the JK flip-flop. So it has, well, essentially it has four inputs, but right now we are just looking at three inputs. So we are assuming that the clear input is inactive, and we are not clearing the flip-flop. So depending on what the values are for J and K, there could be four different possibilities, and hence we could be in one of the four states of the JK flip-flop. When J and K are 0, 0, we are in the store state. When we have K as 1, that means we are killing or resetting the output to a 0. When we have J as 1, we are jumping or setting the output to a 1. And when we are J and K as 1, 1, then we are essentially going to toggle the output. So Q becomes Q complement, which means that whatever it was earlier is going to flip. And when the last thing that we were talking about the last time, we looked at this characteristic table. We also looked at a timing diagram. So we sketched arbitrary waveforms for J, K, and clock, and then we tried to sketch the output of the JK flip-flop, and the only times at which the output had the ability to change was at the negative edge of the JK flip-flop, if we assume that we have a negative edge triggered JK flip-flop that we are working with. So we started with by assuming that the output is 0, and then we went through the cycle by observing, okay, so at the first negative edge we have both K and J as 0 as shown, which means that it is going to be at the store state. So if it was 0 earlier, it's going to continue to be a 0 after the negative edge. Um, and when the second negative edge of the clock happens, both J and K are 1, 1, which means that we are in the toggle state. So Q is going to toggle from 0 to 1 at that moment, soon after that negative edge of the clock. And then the last negative edge in this timing diagram is shown over there, far right, over there. J0K is 1, which means we are in the reset state or the kill state. So Q goes down to 0 or resets to 0. So that's kind of what we have been doing so far in terms of JK flip-flops. And before I go ahead and actually build the circuit um, in part B of experiment 7, I want to talk a little bit about how we are able to implement memory, or the concept of uh, the bit to be stored um, in logic gates. So by using feedback, that's what we talked about in the last class, that we are going to use feedback, and in fact we are going to take advantage of the propagation delay or the gate delay of a logic gate to get memory. So let's see how does that look like. So I'm not going to go through all the details of what is inside a JK flip-flop. My goal right now is to just give you a sense of how the basic elements in memory. So how do we implement memory in circuits? So the element, the basic sequential element that we are going to look at, basic sequential element that we are going to look at over here is a latch. And I'm going to try to look at a NOR based latch. You could also have a NAND based latch. So let's see how this looks like. So let's say I have one NOR gate over here and another NOR gate over there. And let's say I have an input called R over here and an input called S over here. S and R standing for set and reset. And let's suppose I have an output over here and here. Let's call this Q and let's call this QN, for example. Um, so I've drawn two NOR gates and I somehow need to incorporate feedback into this logic diagram to be able to claim that it can uh, store a bit of information. So let's see if I can use some feedback. So I'm going to draw two lines. So let's say I have the input, the other input of the NOR gate. So for the top NOR gate, the input is actually coming from the output of the bottom NAND gate. And similarly, I have the input to the second NOR gate coming from the output of the first NOR gate. So by connecting uh, two NOR gates in a what we call a cross-coupled configuration. So connect two NOR gates in a cross-coupled configuration. The claim is that we can get memory with this. So without going into too much details, I at least want to give you an appreciation towards how we get the memory. And because it is based off of a NOR gate, it is very useful to kind of recollect what a NOR gate is supposed to do. So if I look at a two input NOR gate, say I have one, two input here. So say my inputs are A and B and say the output is X. Doesn't really matter. So if I were to write the truth table, I've got A, B as my inputs and X is my output and four possible combinations over here. And if I had OR between them, my output would be 0, 1, 1, 1. And because I have NOR, I would have 1, 0, 0, 0 instead. So this is wrong. Uh, and this is my NOR truth table. So the goal of this is to write a particular conclusion about the output of the NOR gate in relationship with the inputs. Now notice the output X is 0 here, here, and here. And at those three locations, the input is 1, 1, and 1. So I can write a statement such as this. For a NOR gate, this statement is especially useful in analyzing that latch that we drew on the previous slide. So for a NOR gate, I can write a concluding state remark that output is 0 when any input is 1. Meaning, if I know at least one input to be a 1, then I don't even have to wait for the other input. I know the output is going to be 0. So that's a very helpful uh, statement that we can use in the analysis of the previously drawn latch. So any one input is 1, the output is going to be 0. However, if any one input is a 0, we still need to wait for the other input to come in. Only then we can say anything about the output. So if it is a 0, if the input is a 0, then it doesn't help me. But if the input happens to be a 1, then I don't even have to wait for the other input to come through. I know the output is going to be a 0. So that's where we are going to take advantage of this when we analyze the latch. Okay, so let's move back and take a look at our two NOR gates in a cross-coupled configuration. So let's say I'm going to start simple. I'm going to start with the set state. So let's say I have a set state, meaning I'm going to make this a 1 and I'm going to make this a 0. So let's see what happens if I set those two inputs to a 1 and a 0 respectively. So if I have S as 1, we just now said that even if one of the inputs is a 1, you know that output Qn is going to be a 0. So right away, I can say Qn is going to be 0 right away. Then that 0 actually appears at the input of the top NOR gate. And 0, and there is a 0 there. So 0 NOR 0 will give me a 1 at Q. So I hope you guys are okay with this so far. I started with S as 1 and R as 0, and because S was 1, I didn't even need the other input. I could right away say Qn is 0. If Qn is 0 and R is 0, then my Q will be 1 because of that combination right there. If both the inputs are 0, my output will be a 1. Okay, so let's go back here. So say this is my starting state, right? This is what I have for both the inputs. Now, if we want to see whether we can memorize these outputs as 1 and 0, if you want to claim that this is memory, we have to be able to change the input and still not change the output, right? So even if you change the input, if the output remains as is, then we can claim that we have some sort of memory that we have implemented in this latch. So we do this. Remember what our memory state was? Our memory state was J and K to be both zeros. And it is very similar for an SR latch, a set reset latch that we are looking at, which is a building block to a JK flip flop. So a JK flip flop, you need two SR latches that you connect back to back. We still have those things to talk about, but we implement memory by going from inputs 1 and 0 to let me use a different color here. S changes to 0 and R changes to 0. So let us see what happens when we change the input S to a 0. R was 0, so it will continue to be a 0. So what happens? When I change S as 0, the question is, will this change? Well, the answer to that is, I have changed this particular input to a 0. However, there is still some time before this can change because this changes depending on this, and this is still 0 and question mark. So the output over here is still not fixed. It is still a 1. So that 1 continues to appear over here. And because this is a 1 and this is a 0, this output Qn will continue to be a 0 because one of the inputs is a 1. And this particular 0 appears over here, and it will keep this at 1. So you see what happened here. The reason why this works is because each of these gates has a gate delay. There is a gate delay over here and here, which allows this to happen. So even though we change the input, well, one of the inputs we left as is, we changed one of the inputs, our output, as you can see, remained as is. So this is sort of a very uh, basic view at how we get memory in circuits. That is done by using that cross-coupled configuration, which is sort of a feedback connections. Now, to go from an SR latch, a set reset latch, to a JK flip-flop, we actually need a lot more things. We actually, let's see, I need, say, a latch here and a latch there, one after the other. Latches are by nature level sensitive. So instead of being sensitive to the edge of a clock, they are sensitive to the level of the clock. And by connecting them in a master slave configuration, we call this master slave because one component, the slave, has to wait for the changes in the master to happen. Only then the slave can only respond to the changes done by the master. So that particular configuration allows us to get a edge trigger. So for example, if I have latch 1, so let's call them latch 1 and latch 2, and the latches are very similar to this. There are a few more gates which we are not going to get into, but the basic blocks are this. Gates that are connected in a cross-coupled configuration. So if each of these is a latch 1 and latch 2, say latch 1 is sensitive to the low level of the clock because I claimed that this is sensitive to the level of a clock, and latch 2 is sensitive to the high level of the clock, then I get an edge triggered flip-flop which is sensitive to the low to high edge, because this is sensitive to low, this is sensitive to high, so the overall design is sensitive to the clock going from low to high. So that's how we get edge triggering, which is how we design a flip-flop, by connecting latches back to back. So even though there are lots of details that I have not gone over in this conversation, for those of you who are minoring as ECSE or electrical engineers, you will see all of these things in computer components and operations. So I'm not going to overwhelm you with all those discussions, but I just wanted to give you a sense of what we really mean by memory and feedback, and how does that relate to something that we know by now, which is a NOR gate. Okay, so I'm going to take a moment here for some questions. I want to point out that if you want the analysis that I did for this SR latch is very brief, and it only covers S and R being 1 and 0. I have written up a document. This is again for a different class, but I have written up a document called SR Latch Analysis that goes through all the details of this circuit. So if anybody is interested, I will put this on Piazza, and if anybody is interested, you can take a look at this. This is not a part of EI. It is beyond the scope of EI, but if you're interested, I'm going to give you an opportunity to look at this. Uh, the, the, the question online is, what did the flip-flop mean on the edge trigger? So let's see if I go back here. So you remember in our earlier discussion, when were we changing the output of the JK flip-flop? Well, we were changing the output of the JK flip-flop only after the negative edge of the clock. So I can say that the flip-flop this particular JK flip-flop is sensitive to the edge of the clock, which is different from being level sensitive. I could have also been sensitive to the level of the clock. So for example, when clock is high, I may have some changes in the output. In this case, I don't. So if I'm sensitive to the level of the clock, that is a property of a latch. And if I'm sensitive to the edge of a clock, then that's a property of a flip-flop. In other words, latches are not as precise in terms of timing as flip-flops. Okay, so let's see. Oh, you just wanted to know this. Okay, any other questions? Okay, so we will uh, quickly stop this video and start another discussion. The next discussion in a minute or so is going to be on experiment 7 part B, the building of the flip-flop.